December 14, 1972, the last day any human being has ever stood on the moon. Harrison Schmitt was climbing back into the lunar module after hours on the surface when he noticed something that had nothing to do with geology, which was the reason he had been sent there in the first place. He was a scientist, the only professional geologist ever to walk on another world, and he had spent the day collecting rocks that had not been touched since the solar system was young. But what he remembered afterward was not the rocks. It was a smell. Sharp, dry, like spent gunpowder, the kind that hangs in the air after a rifle fires and does not quite go away. His crewmate Gene Cernan smelled it too. So did the crews of earlier Apollo missions. Several astronauts who brought lunar dust back into a pressurized cabin came back with the same description. Gunpowder, ash, something ancient that had never met air before and did not know what to do with it. Schmitt also started sneezing. His eyes went red. His throat got scratchy. The symptoms faded after a few hours and nobody made much of it, because there were checklists to complete and a launch window to hit and a planet to get back to. But that brief reaction, a sneeze and some red eyes from a few hours of dust exposure, told scientists almost nothing about what repeated exposure would mean over months. Inside a base where the dust came back after every single EVA. Nobody studied it long enough to find out. Schmitt spent less than 75 hours on the moon total. Each Apollo crew stayed for a few days at most. The dust was a footnote, something to mention in the debrief and move past. Here is what that footnote actually means. The Apollo program put 12 human beings on the surface of another world. They drove rovers across ancient craters, collected samples, planted flags, and looked back to see Earth as a small blue circle in absolute black. By any measure, it was the greatest achievement in the history of human exploration. But Apollo was not a moon base. Apollo was a visit. The longest any human being has ever spent on the lunar surface is 74 hours and 59 minutes. That record has stood for more than 50 years. The total time all 12 moonwalkers spent on the surface, every mission added together, comes to just over 300 hours, roughly 12.5 days. That is the entire sum of human presence on another world. You are lying somewhere right now in a place that is keeping you alive without asking anything from you. The air is here. The pressure is here. The temperature is manageable. You did not arrange any of it, and you are not thinking about any of it. This is the story of what happens when all of that goes away. Stand on the surface of the moon and close your eyes for a moment. When you open them, the first thing you notice is the sky. It is black, not the dark blue black of a clear night far from cities. Absolute black, the colour of nothing. Even though the sun is blazing directly overhead, there is no atmosphere to scatter that light into blue. The sun and the stars exist in the same black sky simultaneously, which is something no human eye evolved to process, and something no photograph has ever fully prepared anyone for. The second thing you notice is the silence. Sound requires air. The moon has none. You could stand 2 feet from another person and shout at the top of your lungs and they would hear nothing. The only voice that reaches you is the one piped through your helmet radio. Slightly compressed. Slightly artificial. A constant reminder that the simple act of talking now requires a machine. The third thing you notice, if you stand still long enough, is what is not there. No wind. No smell. No movement anywhere except what you create yourself. The shadow of a boulder falls across the grey dust with a hard edge. No softening, because there is no scattered light to fill it in. The ground under your boots is the same grey it has been for 4 billion years and will be for 4 billion more. Nothing here changes except through the slow accumulation of impacts. One hit at a time, across timescales that make human history look like an afternoon. And the planet that has been quietly keeping you alive your entire life is 384,000 kilometers away. This is the thing about Earth that is almost impossible to feel until you imagine its absence. Earth is not just a place you live. It is a system that works for you every second without being asked. The oxygen in the air you are breathing right now was produced by photosynthesis, happening at this moment in forests and oceans across the planet. Part of a cycle that has been running for billions of years and will continue running without any human involvement. The atmospheric pressure holding your body together is maintained by the weight of a column of air extending 70 miles above your head. The temperature you are sitting in exists within a range compatible with human life because of ocean currents and atmospheric circulation and the precise distance of Earth from the Sun. A set of conditions that took billions of years to arrive at and that you inherited simply by being born here. The magnetic field generated deep in the planet's iron core extends tens of thousands of kilometers into space and deflects the worst of what the Sun sends toward us. The atmosphere above you burns up the small rocks and debris that drift through the inner solar system, turning them into shooting stars that you watch from a blanket on a summer night without once thinking about what they would do if nothing stopped them. Earth is not a location. Earth is infrastructure, the most sophisticated life support system ever assembled, running continuously, for free, with no maintenance required from you. The moon has none of it. A moon base would have to manufacture from scratch every single thing that infrastructure provides. Breathable air, generated and recycled by machines. Atmospheric pressure, maintained inside sealed vessels that must never fail. Temperature regulation, managed by active thermal systems drawing on a continuous power supply. Radiation shielding, because the moon has no magnetic field and no thick atmosphere to soften what comes from the sun and from deep space. Water, extracted from ice deposits that have never been accessed at the surface, and protection from the rocks that Earth's atmosphere burns up before they arrive. Because on the moon they do not burn up. They hit whatever is there at the same speed they travel through space. Most are tiny. Most create nothing more than a microscopic pit on whatever surface they strike. But a moon base would have surfaces exposed to that bombardment every day. Solar panels, radiators, habitat walls, suit visors. The damage is small each time. It accumulates without stopping. Every service that Earth provides automatically, a moon base must provide deliberately. And a service that must be provided deliberately can fail. There is a version of the moon base conversation that stays at the level of inspiration and skips past this part. The frontier spirit, the next giant leap, humanity becoming a multi-world species. That version is not wrong. The inspiration is real and the ambition matters. But inspiration does not filter carbon dioxide out of the air. It does not maintain atmospheric pressure inside a sealed vessel. It does not replace a failed seal at 3 in the morning when the nearest hardware store is 384,000 kilometers away. A moon base is not built on the moon. It is built against the moon. Everything that follows is about what that actually means. The morning started normally. 2 crew members had taken a rover out about 4 kilometers from the base to collect samples from a crater rim they had been working for the better part of a week. The samples were good. The drive back would take maybe 20 minutes. Everything was on schedule, which on a moon base is the closest thing to good news there is. Then a number changed on a display inside one of the helmets. Not a sound from outside. Not a change in the sky. The sun was still blazing in the same black sky it always occupied. The rocks looked identical to how they had looked 5 minutes earlier. The dust was flat and undisturbed in every direction. Nothing in the visible world had shifted in any way that a human eye could detect. But the solar particle flux reading was climbing fast, and the person watching it had trained for exactly this moment. And the training had one instruction above all others. Come back now. Leave the equipment. Come back now. They drove as fast as the rover would move across ground that was not designed for speed. They got inside the base. They sealed the airlock. They moved to the storm shelter, the most heavily shielded section of the habitat, and they closed the hatch. And then they waited. Outside, nothing had changed. The sun still blazed. The rocks still sat. The dust still lay flat in the hard lunar light. But the space between the sun and the moon was now carrying something that would damage living tissue. Something that had been building for hours before any instrument on Earth detected it. Something that arrived without sound, without colour, without any quality that the 5 human senses were built to notice. The most dangerous weather on the moon looks exactly like every other day on the moon. Here is what was actually happening. The sun is not a stable object. It is a churning ball of plasma threaded through with magnetic fields of enormous complexity. And those fields are constantly shifting and occasionally snapping into new configurations that release energy in very short periods of time. When that energy is directed toward the inner solar system, it accelerates particles, mostly protons and electrons, to a significant fraction of the speed of light and sends them streaming outward across hundreds of millions of kilometers. These events are called solar particle events, and the largest ones in recorded history would have been fatal to an unprotected person in space. They are not rare. The Sun produced dozens of significant ones in the last solar cycle alone, and they give very little warning, sometimes hours, sometimes less, arriving before the light that would announce them, if light could announce anything moving at its own speed. On Earth, none of this touches you. The planet's magnetic field deflects the vast majority of these particles before they reach the surface. The atmosphere absorbs much of what gets through. You are protected, every day, by systems that have been running since before complex life existed, and you have never once had to think about them. The moon has no global magnetic field. It has no meaningful atmosphere. When a solar particle event arrives, it arrives at the surface with essentially nothing standing in its way. But here is the part that does not make it into the press releases about going back to the moon. Solar particle events are the acute threat. The storm you can sometimes see coming and take shelter from. If you have a shelter and enough warning, there is a second threat that is quieter, and in some ways harder to manage. Galactic cosmic rays come from outside the solar system. They are high-energy particles accelerated by supernovae and other violent events across the galaxy over billions of years. They arrive from every direction, all the time, day and night, with no warning and no pattern. On Earth, the atmosphere and the magnetic field reduce the dose at the surface to levels that human biology can handle over a normal lifetime. On the moon, the dose is substantially higher, not dramatic on any given day, but accumulating with every week and month a person spends there. What makes galactic cosmic rays particularly difficult to deal with is that they cannot be fully stopped by any material light enough to be practical on a moon base. Lead would stop more of them, but the cost of transporting lead to the moon is staggering, and the weight required for meaningful shielding is not realistic with any near-term launch system. Water is a better shielding material by weight for this type of radiation, and water is something a base would need anyway. But the quantities required are enormous. The most practical solution engineers have settled on is the moon itself. Burying habitats under several meters of lunar regolith would substantially reduce the radiation dose to the people inside. The material is free. It is everywhere. Robotic excavators could pile it over a habitat structure once that structure is in place. This is one of the better arguments in the entire moon base conversation. But burying a habitat does not solve the problem for crew members who are outside when a warning comes. Picture the storm shelter that the 2 crew members retreated to on that ordinary morning. It would not feel the way people imagine emergency shelters feel in movies. It would be a narrow, windowless compartment wrapped in water tanks and food stores and layers of regolith above it. Not designed for comfort, designed for waiting. The crew would sit in there while nothing outside appeared to happen, trusting instruments over instincts. Because the human body has no native sense for this kind of danger. No pain, no heat, no warning signal from any nerve ending, just a number on a screen telling you that the invisible has turned hostile. When the all clear came, they would go back to work. They would pick up the schedule where they left off. And the next morning, the sun would look exactly the same as it always did. That is the thing about radiation on the moon that no photograph and no artist rendering conveys. It does not look like anything. The most dangerous condition in the environment above the base is indistinguishable from a calm, clear day. The crew learns to trust instruments they cannot feel, to respond to warnings their bodies cannot generate. to take seriously a threat that never once announces itself through any of the channels that human beings evolved over millions of years to read. On Earth, danger usually announces itself. A storm builds on the horizon. Smoke reaches you before the fire does. Even small physical threats. A step that gives way. A car that swerves. Produce a visible signal before the impact. The nervous system evolved in a world where danger had a form you could recognize. On the moon, it can arrive without changing the view. 4.5 billion years ago, when the solar system was still sorting itself out and collisions between large objects were common, something the size of Mars hit the early Earth. The debris from that collision eventually coalesced into the moon. Since then, the moon has been doing one thing consistently: getting hit. Not by objects large enough to make headlines. By small things. Constant small things. Rocks and particles drifting through the inner solar system. Striking the lunar surface at high velocity every day across the entire 4.5 billion year history of the moon. No wind to carry the debris away afterward. No rain to wash it down slopes. No biological processes to break it down or bind it into soil. Just the slow, patient accumulation of impact after impact, grinding the surface layer of the moon into something that looks, from a distance, like grey dust. Up close, it is something else entirely. Each particle is a fractured fragment, sharp, the way freshly broken glass is sharp, with edges that have never been worn down by water or wind, because there has been no water or wind to wear them. They carry an electrostatic charge from continuous bombardment by solar wind particles, which makes them cling to surfaces with a persistence that ordinary dust does not have. They do not fall the way dust falls on Earth. They drift. They float. Under some conditions, electrostatic charging may loft fine particles above the surface, creating a subtle movement that scientists are still working to fully understand. What is understood is that the particles go where nothing on Earth would allow them to go, into seams and joints and gaps that seem impossibly small, onto surfaces that seem to have no reason to be coated. The Apollo astronauts discovered this within hours of their first moonwalks. After each EVA, the crews brought their suits back into the lunar module and the dust came with them. It coated every surface it touched. It scratched visors. It worked its way into the joints and bearings of the suits faster than anyone had predicted. And it produced that smell, the spent gunpowder that Harrison Schmitt and several of his colleagues remembered years later as one of the most distinctive details of the entire experience. Now, here is what the brevity of Apollo prevented anyone from studying seriously. Think about what lunar dust is made of. It is pulverized silicate rock with edges sharp enough to cut at the microscopic level. When Schmitt sneezed in the cabin of Apollo 17, his body was reacting to particles that had never in 4.5 billion years encountered a respiratory system. The immune response knew something was wrong but had no prior experience to draw on. The symptoms faded. Everyone moved on. What nobody could answer then, and what nobody can fully answer now, is what happens to a set of lungs that encounters that material not once but dozens of times. Every day. For months, the particles are the right size to penetrate past the upper respiratory defenses that catch larger things. Once they are deep in the lungs, the body cannot break down silicate glass. It cannot dissolve them. It cannot expel them through any normal process. Studies of workers in industries that produce fine silicate particles have not produced encouraging findings. The comparison is imperfect. The materials are different. But the principle, sharp silicate particles accumulating in lung tissue over time, has a track record that the medical community does not consider benign. The dust does not stop with the body. It goes after the machines. The seals on an airlock are designed to create an airtight barrier between the pressurized interior and the vacuum outside. Those seals depend on clean, smooth contact surfaces, lunar dust particles, working their way into those contact surfaces with every cycle of the airlock, create microscopic scratches and pits that reduce the seal's effectiveness over time. A seal that leaks even slightly on the moon is not an inconvenience. It is the beginning of a pressure loss that the life support system has to compensate for, drawing on reserves that were sized for emergencies, not continuous supplementation. The joints in a spacesuit that allow the wearer to bend and reach are vulnerable to the same process. The Apollo crews noticed their suits becoming harder to move as dust worked into the mobility elements during their brief surface stays. On a long-duration base, with EVAs happening multiple times per week, the cumulative wear on every joint, every bearing, every sealing surface would have to be tracked and managed continuously. Solar panels accumulate a layer of dust that reduces their output. This is not hypothetical. The Apollo program left retroreflectors on the lunar surface, precisely positioned mirrors that scientists still use to measure the exact distance to the moon by bouncing laser beams off them. Measurements taken over more than 50 years show a gradual decline in the reflective efficiency of those mirrors. The most likely explanation is a thin layer of dust that has been settling on the surfaces since December of 1972, with no weather to clean it off, no one to wipe it down, accumulating one particle at a time across 5 decades of slow drift. Baked into every EVA, every airlock cycle, every suit brought back inside the base, is the same negotiation. The interior world, the base, is trying to maintain against the exterior world the moon is trying to impose. The protocols for managing that transition would be among the most constant rhythms of life on the base, as unavoidable as eating and sleeping. The dust that was a footnote in 3 days of Apollo operations becomes, over months and years, a central fact of survival. Filters can capture some of it. Cleaning protocols can reduce how much gets in. Engineers can design suit ports that minimize contact between the suits and the interior atmosphere. None of these solutions eliminate the problem. They manage it. Imperfectly. Continuously. With the understanding that the moon is patient and the base has to be more patient still. The first enemy of a moon base is not a dramatic disaster. It is the moon itself, ground into powder, carried across every threshold, and slowly entering every system meant to keep humans alive. 6 months into the first long-duration moon base mission, a pressure sensor in the water recovery system flagged an anomaly. Not a big one, a small one, the kind that in a normal engineering environment would generate a work order and a 2-day wait for a technician, the kind that on Earth you would note in a log, schedule for repair, and largely forget about until the appointment. On the moon, the base commander gathered the crew. The water recovery system fed the electrolysis unit that split water into hydrogen and oxygen. The oxygen went into the habitat atmosphere. The hydrogen went into storage. The electrolysis unit had been running at full capacity because the base was in its 6th month and the crew was consuming resources at the high end of the predicted range. A reduction in water input meant a reduction in oxygen output. The life support system would compensate by drawing on the stored oxygen reserves. The stored reserves were sized for emergencies, not for continuous supplementation over days or weeks. Meanwhile, the water reduction was affecting the cooling circuit that ran through the battery array. The batteries were already working harder than the design baseline because a dust accumulation on 2 of the solar panels had reduced power generation by about 7% over the previous 3 weeks. Working harder meant generating more heat. More heat meant more demand on the cooling circuit that was already short on water. None of these problems was catastrophic individually. Each one, looked at alone, was manageable. The problem was that none of them was alone. This is the thing about a moon base that no artist rendering ever shows. The renderings show a habitat on a grey landscape, clean lines, airlocks and solar panels and a rover parked outside. The image communicates a place, a location, somewhere you could imagine living. What it does not show is that every wall of that habitat is the outer boundary of a machine that has to run continuously, that every system inside it is connected to every other system, and that the moon is working on all of them simultaneously. A house on Earth is passive. It provides shelter from weather and a place to sleep. The planet does everything else. The air comes from outside. The pressure that holds your body together is maintained by a column of atmosphere that extends 70 miles above your head and has nothing to do with whether the roof leaks. The temperature inside your house is a modification of the temperature outside, adjusted by burning fuel or running electricity. But the baseline is provided by the planet for free. Remove the house and you are uncomfortable. Remove the planet and the house becomes a pressurized coffin. On the moon, the box is all there is. A moon base has to manufacture every molecule of breathable air, either brought from Earth or extracted locally through processes that require energy and machinery and maintenance. The atmospheric pressure has to be actively held inside sealed vessels. Every wall under constant stress against the vacuum outside. Every seal, a point where that stress concentrates. The temperature has to be managed by active systems because the lunar surface swings between 127 degrees Celsius in direct sunlight and negative 173 in shadow. And no passive insulation handles a 300-degree range indefinitely. Carbon dioxide exhaled by the crew builds up in the closed atmosphere and has to be chemically scrubbed before it reaches toxic concentrations. Water has to be captured and recycled with an efficiency that no Earth-based system has ever needed to achieve. Waste has to be processed in ways that return usable material to the habitat loop rather than simply being discarded. Because on the moon there is nowhere to discard anything. Every one of these functions requires machinery. Every piece of machinery can fail. And on the moon, when machinery fails, the consequences do not stay neatly inside the system that failed. Engineers have a name for what happened that morning with the pressure sensor. They call it a cascade. One system develops a problem, and that problem changes the operating conditions for another system, which changes conditions for a third, until what started as a small anomaly on one sensor has become a situation the entire crew is managing at once. Cascades are common in complex interdependent systems. On Earth, they are serious. On the moon, they are existential. The water system was repaired in about 4 hours. The crew replaced a degraded seal in a junction fitting, one of 12 spares they had brought for that specific component, based on a failure probability analysis done 18 months before launch. The oxygen reserves were drawn down by about 9% during the repair window. The cooling circuit was rerouted through a secondary loop while the primary was offline. Everything was back to normal by dinner. But the base commander noted in her log that night that they had used one of 12 seals for that fitting, that the resupply mission carrying more was still 4 months away, and that the failure analysis had not accounted for the higher dust accumulation rate they were actually experiencing, which was accelerating wear on several other seal types as well. Comfort on the moon is not the opposite of danger. Comfort is danger being delayed by machinery. The moment the machinery stops delaying it, the danger is right there, unchanged, having waited with the patience that only a vacuum can maintain, before that machine can even begin to run. Though, the moon presents a problem that most people never think about, getting there without destroying what you just built, and that problem starts before the first human being ever sets foot inside. Every journey in human history has required a place to land. The Polynesian navigators who crossed the Pacific in double-hulled canoes needed a beach. The ships that carried the first European settlers to North America needed a harbour. Every airport ever built exists because flight is one thing and arrival is another, and the gap between them requires infrastructure that has to exist before the travellers do. The moon will require the same thing. The difference is that on the moon, the harbour has to be built by the first ship that arrives. Here is the problem that this creates, and why it is more serious than it sounds. When a rocket engine fires near the surface of the moon, it is not simply pushing a vehicle downward the way an aircraft lands through atmosphere. There is no atmosphere. The exhaust plume from a descending rocket hits the lunar surface directly, and what it does to that surface is something that surprised engineers the first time they modelled it carefully. The exhaust spreads outward across the regolith at high pressure. The surface is covered in loose fine particles, the same fractured silicate dust discussed in the previous chapter. When the exhaust hits that material, it accelerates the particles outward in all directions, not like a sandstorm, where wind carries debris at speeds your hand could stop, but like a horizontal spray of tiny projectiles moving at several hundred meters per second, with nothing in their path to slow them down. On Earth, Atmosphere would catch those particles within meters. On the moon, they keep going. Studies modeling rocket plume behavior on the lunar surface suggest that ejecta from a landing can reach targets several kilometers away and arrive with enough kinetic energy to cause real damage. A solar panel struck by regolith particles at several hundred meters per second does not collect dust. It gets sandblasted. A radiator surface hit by the same particles loses thermal efficiency. A seal on a habitat wall, struck enough times, develops the kind of microscopic wear that the dust chapter already established is a slow-motion threat to everything the base depends on. Now think about what a permanent base actually requires. It is not a destination you visit once. It is an operation that needs a continuous flow of cargo from Earth, food and equipment and spare parts and everything else that cannot yet be produced on the moon. Every resupply mission means another rocket descending toward the surface. Every descent means another round of high-velocity regolith blasting outward from the landing point. If the landing site is close to the base absorbs that bombardment with every delivery. The act of resupplying the base slowly damages the base. A cargo lander might arrive carrying exactly the replacement seal the base needs. But if the act of delivering that seal scratches the radiators and coats the solar panels and sends another layer of abrasive particles toward the habitat walls, then resupply has become a form of wear. The base is being saved and damaged by the same event. The solution engineers have identified is a prepared landing pad. A hardened surface that absorbs the exhaust without generating dangerous ejecta. On Earth this is straightforward. You have concrete, asphalt, an entire industrial civilization with centuries of experience building surfaces for vehicles to land on. On the moon you have regolith and vacuum and sunlight. The most promising approach is sintering, using concentrated heat to partially melt the surface particles and fuse them into a solid layer. Focused solar energy can do this in principle. Microwave systems have been proposed. Robotic equipment that physically compacts and stabilizes the surface has been tested in simulation. Each method has worked to some degree in controlled conditions on Earth. Each method also requires equipment that has to be sent to the moon before the landing pad exists, which creates a sequencing problem that has no clean solution. The first mission to build the landing pad has to land somewhere. Wherever it lands is exposed to the same plume ejecta. The landing pad is meant to prevent. The infrastructure that makes safe landing possible has to be installed by a mission that lands without it. There is also the question of distance. Land too close to the base and you damage it with every delivery. Land too far and you need a transportation system to move cargo from the landing zone to the habitat. That transportation system needs a route. The route needs a surface stable enough for repeated vehicle travel. A rover driving across loose regolith kicks particles into ballistic trajectories that, in vacuum, carry them much farther than intuition suggests. The road between the landing zone and the habitat, if it is not prepared, becomes another source of the same damage the landing pad was designed to prevent. Every solution creates requirements. Every requirement competes with every other requirement in a budget and a launch manifest that are always tighter than the ambition they are trying to serve. What this particular challenge reveals is something worth holding on to for the rest of this story. The moon-based conversation tends to happen at a level of abstraction, where each problem sounds like a project, something to be assigned to an engineering team and solved before the next step. The landing pad sounds like a project. Dust mitigation sounds like a project. Radiation shielding sounds like a project. But these are not independent projects. They are facets of a single continuous problem, which is that the moon does not provide any of the conditions that make human presence possible. And building those conditions from scratch in a place you cannot easily reach or resupply or repair creates a web of dependencies where every solution touches every other solution, and the cost of getting one wrong is not a failed project, but a failed mission. Before the moon can have a home, it needs a place where arrival does not become destruction, and that place has to exist before anyone arrives to need it. You have never, in your entire life, experienced a sunrise as anything other than inevitable. It has happened every day you have been alive. It happened every day your parents were alive, and their parents before them. all the way back to the first human being who ever looked east and waited. The sun coming back is not an event you prepare for. It is a condition of existence so fundamental that your body has been calibrated to it at the cellular level. A 24-hour rhythm woven into your hormones and your sleep cycles and your core temperature and your sense of time itself. On the moon, the sun coming back is something you count down to. Across most of the lunar surface, a full day lasts 29.5 Earth days. That means roughly 14.5 days of continuous sunlight. The sun moving in a slow arc across the black sky without ever setting. Shadows swinging gradually around rocks as the hours pass. And then 14.5 days of darkness. Not the darkness of a winter night with stars overhead, and the comfortable knowledge that morning is coming in a few hours. Extended, total darkness. 2 full weeks with no sunlight at all, near the lunar South Pole, where early bases are most likely to be built. The pattern is more complicated, but not necessarily easier. Some elevated ridges catch sunlight for a higher fraction of the year because of the low angle at which the sun moves along the horizon at those latitudes. A few locations receive illumination for perhaps 80 to 90% of the lunar year, which is better than the stark 2-week cycle at lower latitudes. But 80 to 90% means there are still periods of days to weeks with no sun. The terrain that offers the best illumination is not always the same terrain closest to the water ice deposits in the permanently shadowed craters nearby. Getting both, light and ice, often means accepting significant distance between them, with all the transportation and cable infrastructure that implies. And the shadows themselves are a hazard. With the sun so close to the horizon at the poles, even modest terrain features cast long shadows. A boulder that would be unremarkable anywhere else can block sunlight from a solar array for extended periods. Siting a power system at the poles requires detailed terrain analysis at a level of precision that orbital surveys have not yet fully provided for the areas of greatest interest. Solar power is the obvious answer to powering a moon base. The moon has no clouds. The sun delivers consistent energy to the surface during the long lunar day. The appeal is real and the logic is sound. Until the sun goes down, a base that runs on solar power has to store enough energy during the lunar day to operate through the lunar night. Every system in the base, life support, thermal control, lighting, computers, communications, water processing, medical equipment, has to keep running for up to 2 weeks with no input from the sun, not for a few hours during a cloudy afternoon, for 14 days, continuously, without interruption, because an interruption in life support on the moon is not an inconvenience. The amount of energy storage required to do that is not a software problem or an engineering creativity problem. It is a chemistry and physics problem. And chemistry and physics impose hard limits on how much energy a battery can store per kilogram of its own weight. At current battery technology, providing 14 days of power storage for even a modest base with a small crew would require a battery system measured in many tons. Every ton of that has to be launched from Earth, transported across 384,000 kilometers of space, and landed on the surface without incident. The numbers do not stay manageable for long when you follow them out. Nuclear power is the alternative that avoids those numbers entirely. A fission reactor does not care whether the sun is up. It produces power continuously, at a predictable rate, for years. Ground demonstrations of compact fission concepts, including systems developed under NASA and Department of Energy programs, have shown that small reactors in the range needed for an early outpost are technically feasible. The concept is sound, but operating a concept on the ground in Nevada is not the same as operating a dependable power system on the lunar surface. A reactor requires shielding to protect the crew from its radiation output, which adds mass to an already constrained weight budget. It requires a cooling system to manage the heat it generates, which is a separate set of components that can fail independently of the reactor itself. It requires specific protocols for deployment, for monitoring, for emergency scenarios that the crew would have to manage without being able to call in a specialist team from the nearest national laboratory. A reactor malfunction on the moon is handled by whoever is there. with the training they brought and the tools they have on hand. Then there is the thermal problem that has nothing to do with power generation. When the lunar night arrives and the surface temperature drops to negative 173 degrees Celsius, that cold does not stay outside. It conducts into anything touching the ground. It radiates toward any surface facing the cold landscape. Equipment left outside during the lunar night is subjected to temperature swings that no Earth-based engineering has routinely had to account for. Metals contract. Lubricants stiffen. Seals that were calibrated at one temperature behave differently at another. And a seal that behaves differently than expected on the moon is the beginning of a problem the base cannot afford. Rovers left outside have to be designed to survive those temperatures or brought inside before darkness falls, which requires a pressurized garage that adds to the base's footprint and complexity. Pipes between habitat modules have to be insulated against the cold or actively heated, which draws power that is already under pressure during the night. Solar panels that stay deployed through the thermal cycle, heating to more than 100 degrees in daylight and cooling to nearly negative 200 in darkness, undergo material stress with every cycle, and stress applied repeatedly to any material eventually produces failure. The lunar night is not a feature of the environment that a moon base works around. It is an engineering event, a scheduled crisis that the base has to be designed, built, and operated to survive, month after month, for as long as anyone lives there. On Earth, a blackout is a crisis. On the moon, it is the beginning of a countdown. In September of 2009, a NASA spacecraft called L-Cross deliberately crashed into a permanently shadowed crater near the moon's south pole and sent a plume of material high enough for instruments in orbit and on Earth to analyze. Among the compounds detected in that plume was evidence of water, confirmation that ice and other volatiles had been preserved in that permanently shadowed region across billions of years of deep cold. The headlines were enthusiastic, and they were earned. The discovery was real. Scientists who had spent years arguing that water ice might exist in those craters had their best evidence yet. Water on the moon changes the economics of everything that follows, because water is oxygen to breathe and hydrogen to burn, and a radiation shield you can fill walls with, and a resource that does not have to be launched from the surface of the Earth. The headlines were right about what was found. They were quieter about what finding it actually means. Start with where the water is. The permanently shadowed regions near the South Pole are craters whose geometry prevents sunlight from ever reaching their floors. The sun at the poles moves along the horizon, and the rims of large craters catch that low-angle light while the interiors remain in permanent darkness. In that darkness, temperatures can drop to around negative 250 degrees Celsius, cold enough to trap and preserve water molecules that arrived over billions of years on comets and asteroids, or were produced by reactions between solar wind particles and oxygen-bearing minerals in the soil. Negative 250 degrees Celsius is close to the coldest temperature that exists naturally in the solar system. Most current robotic systems would require major redesign to work reliably in conditions that cold. Batteries lose most of their capacity at those temperatures. Electronics calibrated for operating ranges that assume some minimal warmth behave unpredictably below their design floor. A rover that drives into a permanently shadowed crater to mine ice may find that its power system does not function the way it did at the warmer temperatures outside the crater rim. The ice itself is not sitting in a convenient layer waiting to be scooped up. The current understanding, based on orbital data and the L-Cross results, is that water is mixed into the regolith at concentrations that vary significantly from place to place, and may be as low as a few % by weight in many areas. Mining water from the lunar poles is not like drilling into a glacier. It is more like trying to wring moisture from frozen gravel, one scoop at a time, in the coldest and darkest accessible place in the inner solar system, with equipment that was not originally built for those conditions. Assume you solve the extraction problem. The raw material you have collected is not water. It is excavated regolith, containing some percentage of ice along with other frozen compounds that accumulated in the cold trap alongside the water over billions of years. Separating the water from everything else requires heating the material enough to vaporize the ice while capturing the vapor before it escapes into the lunar vacuum. Heating requires energy. Capturing vapor requires sealed processing equipment. Every step is a system, and every system can fail. Now follow the water further. Because water on a moon base is not just for drinking. The oxygen the crew breathes comes from water. Electrolysis. Splitting water molecules into hydrogen and oxygen using electricity is the most reliable method available for oxygen generation in a closed environment. The process requires continuous power. The oxygen goes into the habitat atmosphere. The hydrogen can be stored as a fuel or vented, depending on the base's needs. Water has been proposed as a radiation shield. Its hydrogen content makes it effective at scattering the energetic particles of galactic cosmic rays, better than most metals by weight. Walls filled with water could provide meaningful protection to sleeping quarters and storm shelters. But water tied up in the walls is not available for life support or oxygen generation, and the quantities required for even modest shielding are substantial. The water budget of a base is pulled in multiple directions simultaneously. And then there is the ambition at the center of most conversations about lunar water, the one that appears in almost every justification for choosing the South Pole. Using locally extracted water to produce rocket propellant, liquid hydrogen and liquid oxygen are among the most powerful propellants available. A base that could manufacture its own propellant from local water would not need to import propellant from Earth for return trips or outbound missions. The economic logic is compelling. It is one of the strongest arguments for building at the South Pole, rather than somewhere more accessible. The logic is sound. The challenge is in what manufacture actually requires. Ice, extracted from a crater at negative 250 degrees, processed to separate water from regolith and contaminants, purified and tested to confirm it is safe to use, electrolyzed into hydrogen and oxygen, liquefied, because gaseous hydrogen and oxygen at ambient temperature are not rocket propellants. Cryogenic liquids are, stored in insulated tanks that must maintain temperatures colder than the lunar night to keep the propellant from boiling off, transferred to the vehicle that needs it without loss. Ice, then extracted material, then captured vapor, then purified water, then electrolysis, then liquefied gases, then cryogenic storage, then propellant transfer. Each arrow in that chain is a machine. Each machine needs power. Each machine needs maintenance. Each machine needs spare parts. Each machine can fail, and if any machine in the chain fails at the wrong moment, every step that comes after it stops. None of this chain has been demonstrated at useful scale on the lunar surface under actual lunar conditions. The orbital data confirms that water ice exists. The ground truth, how accessible it really is at specific sites, how concentrated it is, whether the extraction and processing technologies tested on Earth will function in the actual cold and vacuum of the South Pole, is still waiting for missions that have not yet flown. There is a version of the moon base story where the water question is essentially solved, where the ice is rich and accessible and the technology to use it is mature, and where mission planners are working on other problems. That version appears in optimistic program summaries. The more honest version is this: finding water is not having water. Having water is not using water. Using water is not producing propellant. And producing propellant is not a moon base that does not need Earth. Each of those steps is real work, waiting to be done, in a place where doing it will be harder than any test on the ground has yet confirmed. Most households have a drawer somewhere. It usually lives in the kitchen or the garage, and it contains things like spare batteries, a few extra fuses, electrical tape, a handful of screws that came with furniture you assembled years ago and seemed too important to throw away. The particular kind of person who keeps that drawer well stocked is not preparing for disaster. They are acknowledging something that most people prefer not to think about: the systems we depend on are not permanent, and the gap between a system failing and a system being repaired is bridged by whatever you happen to have on hand. On the moon, that drawer has to contain everything: the right version of everything, and it has to have been packed on Earth, years before the failure it is meant to address. It was not a dramatic morning when the base found this out in a way that stayed with everyone. No solar storm warning had come through. The dust readings were within normal range. The power system was running on its standard cycle. One of the crew had made coffee, and the 6 of them were moving into their work assignments with the quiet efficiency that comes from months of shared routine. Then a carbon dioxide sensor flagged a reading that was slightly higher than the previous day, which had been slightly higher than the day before. Nobody was in danger. The scrubber was still removing carbon dioxide from the atmosphere. It was just doing it a little less efficiently than it had been doing it 3 weeks ago. And the trend line, if you looked at it the way the base physician had been looking at it, was pointing somewhere that required attention before it required emergency response. Diagnostics showed reduced efficiency in one of the absorbent beds in the carbon dioxide removal system. The material that captured carbon dioxide molecules and held them for venting had degraded faster than the mission timeline had predicted. It needed to be replaced. On Earth. This is a 2-day problem. You contact the supplier, describe the issue, receive a replacement component, and a technician installs it in an hour. The total disruption is a work order and a small invoice. The first question on the Moon is not how long the replacement will take. The first question is whether the replacement exists on the base. Spare parts planning for a Moon base is one of the most demanding logistical exercises in the history of human engineering, and it is demanding in a way that is categorically different from anything Earth-based operations face. Every component of every system in the base has a failure rate, an expected service life, a set of conditions under which it will wear out faster than the baseline. The planning team has to model all of those failure rates simultaneously, across hundreds or thousands of individual components, and decide how many spares of each to stock, knowing that every spare is mass that has to be launched from Earth, and every spare not stocked is a potential gap that a future crew will have to improvise around. The absorbent bed material was in the inventory, 3 replacement units, which the pre-mission analysis had estimated as sufficient for the planned tour duration. The crew installed one that morning and the scrubber returned to normal efficiency by afternoon. The base commander logged the replacement and noted that they now had 2 remaining units of that type, that the resupply mission carrying more was approximately 4 months away, and that the degradation rate they had actually observed was about 30% faster than the model had predicted. Whether that was because of higher crew activity levels, or the dust environment, or some interaction between the two that the model had not accounted for, was unclear. 2 units remaining, 4 months until resupply, degradation rate running faster than predicted. These 3 facts sat in the log alongside the notation that 7 other consumable components were also running ahead of their predicted usage curves. This is not a failure of planning. It is the nature of operating in an environment where almost every variable is still being learned. The mission planners did the best analysis they could with the available data. The available data was incomplete because nothing like this had been done before. And incomplete data produces predictions with error bars. And error bars have a way of resolving in the unfavorable direction, when the thing you are predicting is a complex system under novel stresses. What it means in practice is that a moon base is never simply operating. It is always simultaneously operating and measuring the gap between what it predicted and what is actually happening, and adjusting its future predictions accordingly, and hoping the adjustment happens before the gap becomes a crisis rather than after. The Apollo 13 crew faced a version of this in April of 1970, 3 days into the mission to land on the Moon. An oxygen tank in the service module exploded. The damage knocked out most of the command module's power and eliminated the oxygen supply for the fuel cells that generated that power. The crew moved into the lunar module and used it as a lifeboat for the 4 days it took to return to Earth. The carbon dioxide removal system in the lunar module was not designed for 3 people over 4 days. It began to saturate. The carbon dioxide level in the cabin started rising. The solution required the crew to build an adapter connecting the command module's square carbon dioxide filters to the lunar module's round filter receptacle, using materials available on the spacecraft: cardboard from a flight manual, plastic bags, duct tape, a sock. The improvised adapter worked. The crew survived. That improvisation became one of the most celebrated moments in the history of human spaceflight, and it deserves every bit of that recognition. But it also deserves to be understood clearly for what it was. It was the moment when the logistics strategy failed and human ingenuity stepped in to prevent the failure from becoming fatal. Improvisation under pressure is not a logistics strategy. It is what you do when the logistics strategy has run out. A moon base that relies on improvisation as its primary response to component failure is a moon base that is one bad day away from a situation that cannot be improvised through. Three-dimensional printing offers some help, and the development of additive manufacturing systems for space applications is real and ongoing. But a field printer cannot yet reliably reproduce the dimensional tolerances and material properties of precision-engineered seals and bearings and optical components. A seal that is slightly the wrong size does not fail immediately. It fails at an unpredictable time, under load, when the circumstances make the failure most consequential. The base from that unremarkable morning continued its mission. The carbon dioxide scrubber ran on the replacement unit. The inventory report went into the next resupply manifest. The base commander finished her log entry and moved on to the rest of the day, which had its own list of maintenance tasks and scheduled EVAs and data to review. But even a healthy base is always one step ahead of the failures it has not yet experienced. The work of staying alive on the moon is not dramatic most of the time. It is the work of a drawer that has to be stocked before the failure arrives, by people who are not yet there, for systems that have not yet broken, in a place where the cost of getting it wrong has no margin for sentiment. Civilization on the moon may begin not with a city, but with a drawer full of replacement seals, and the discipline to notice when one is beginning to fail. But even if every machine is maintained perfectly, the base still depends on one system that no engineer can fully redesign: the human body. Valery Polyakov landed in Kazakhstan on March 22, 1995. After 437 days on the Mir space station, he had set the record for the longest continuous human spaceflight in history, a record that still stands. When the recovery team opened the capsule hatch and reached in to help him out, he waved them off. He had decided before landing that he was going to walk out on his own. He wanted to demonstrate, to himself and to everyone watching, that a human being could spend 14 months in space and come back functional. He made it out of the capsule. He sat in the recovery chair. And then, by his own account, he realized that what he had planned and what his body could deliver were not the same thing. The muscles that kept him upright on Earth had spent 14 months in an environment where upright did not require effort, and they had quietly, without drama or announcement, become something less than what they had been. He recovered, fully. Over several months, he went on to live a long and healthy life. But that moment, a man who had trained for years and maintained a rigorous exercise program throughout his mission, discovering on a landing field in Kazakhstan that his body had changed in ways he could not will away, is one of the more honest portraits of what extended spaceflight does to a person. The International Space Station has given us 25 years of data on what happens to human beings in microgravity over periods of 6 months to a year. Bone mineral density declines at rates that are significantly faster than age-related loss on Earth, even with the 2 hours of daily resistance exercise that station crew members are required to perform. Muscle mass decreases despite those protocols. Fluid shifts toward the upper body change the pressure environment inside the skull. A condition now studied as spaceflight-associated neuroocular syndrome has been documented in a significant fraction of long-duration astronauts, involving structural changes in the eye and optic nerve that in some cases do not fully resolve after return to Earth. This is what happens in zero gravity. The Moon is not zero gravity. The Moon's gravitational pull is roughly 1/6 of Earth's. That is enough to give objects weight, and enough to make the experience of standing on the Moon feel meaningfully different from floating in an orbiting spacecraft. 1/6 gravity is not nothing. The question, and it is a question that nobody can currently answer with data, is whether it is enough. Enough to slow the bone density loss that microgravity accelerates, Enough to keep the cardiovascular system from the adaptations that the station data documents. Enough to prevent the fluid shifts that change pressure inside the skull. Enough for a pregnancy. Enough for a child to develop a skeleton and a cardiovascular system that would still function if that child ever returned to Earth. These are not hypothetical questions for a distant future. They are questions that would begin generating answers the moment the first long-duration crew settles into a moon base for a stay measured in months rather than hours. The first long-duration crews would be operators, explorers, and inevitably participants in one of the most consequential biological studies ever conducted. Their bodies would be the primary data source for questions that ground-based research and orbital spaceflight cannot answer, because the specific variable being tested, 1/6 gravity sustained over months, has never been experienced by any human being for long enough to produce meaningful data. Every bone scan, every cardiovascular assessment, every vision test administered during the mission would be adding to a dataset that does not yet exist. The exercise question alone represents a significant operational burden. Station crew members spend roughly 2 hours per day on structured physical activity, using equipment specifically designed for the microgravity environment. That is 2 hours out of every operational day that is not available for the scientific and engineering work the mission exists to accomplish. On the Moon, the exercise requirement may be different in ways that are not yet understood, requiring different types of loading and different protocols to address whatever patterns of physiological change 1/6 gravity actually produces. Those protocols will have to be developed in real time, refined as data comes in, and updated whenever the data suggests the current approach is not sufficient. And then there are the questions that extend beyond individual physiology into territory that feels more like philosophy than medicine, but is neither. If a moon base becomes a place where people raise children, the 1/6 gravity question stops being about occupational health and becomes something larger. A skeleton develops in response to the gravitational loads placed on it during growth. A cardiovascular system calibrates itself to the demands of the environment it develops in. Sensory systems learn to interpret gravitational input during the period when the nervous system is most plastic. A child who grows up in 1/6 gravity is not growing up in the environment that shaped the species. What they become, physically, is an open question. And open questions about child development in novel gravitational environments are not the kind of thing you test and then adjust. They are the kind of thing that unfolds across years and only reveals itself fully in retrospect. The moon is not weightlessness, but it may not be enough weight to keep us fully human. And we may not know the answer until human beings have lived there long enough for the moon to begin answering back. That answer, whatever it turns out to be, will arrive the same way most important answers arrive on the moon. Slowly, through data generated by people who are already committed, in a place where the commitment cannot easily be reversed. Before you step outside, you spend 45 minutes getting dressed. Not dressed the way you get dressed on Earth, where the whole process takes a few minutes, and the worst consequence of doing it carelessly is a mismatched outfit. This is a different kind of process. You start with the liquid cooling garment, a tight layer threaded with small tubes that will carry water across your skin to manage the heat your body generates when you work. Then the lower torso assembly, a rigid structure housing the legs and the waist. Then the hard upper torso, which you lower yourself into from above while your crewmate checks every connection. The gloves attach with a twist and a click that you verify twice and then verify again. The helmet locks on. The visor comes down. Then your crewmate goes through the checklist with you, point by point. Every seal, every pressure reading, every system status, because the person getting dressed cannot see most of what needs to be verified. And because the cost of getting something wrong is not a cold morning, the airlock cycles. Pressure drops to nothing over a few minutes. The outer hatch opens. You step out into a place where the suit you are wearing is the only thing standing between you and an environment that would kill you in under 2 minutes without it. What you are wearing is not clothing. It is the smallest moon base ever built. A spacesuit for lunar surface operations has to do everything the habitat behind you does, compressed into something a human being can move around in for 6 to 8 hours. It maintains an internal pressure sufficient to keep the body functioning, held against the complete vacuum outside by layers of fabric and sealing surfaces that must hold without failure for the duration of every EVA. It supplies oxygen at a controlled rate while removing the carbon dioxide the wearer exhales before it builds to toxic concentrations. It manages the heat the body generates during physical work. Because in vacuum there is no convective cooling, and without the water tubes in the cooling garment, the core temperature would climb to dangerous levels within an hour of moderate exertion. It shields the wearer from radiation. Imperfectly, providing some protection but not the equivalent of the habitat's shielding. It offers a layer of protection against the micrometeorites that arrive without warning, not by stopping everything, which would require armor too heavy to move in, but by providing enough layered material that the most common particle sizes are slowed before they reach the pressure garment. It allows the wearer to see through a visor coated to filter the unattenuated solar radiation that would otherwise damage unprotected eyes in that unfiltered environment. And it has to let you work, bend and reach and lift and turn bolts and adjust instruments and handle tools in a pressurized garment that, without deliberate engineering at every joint, would behave like an inflated balloon and resist every movement. That last requirement is where the fundamental tension of spacesuit design has lived since the beginning of human spaceflight, and it has never been fully resolved, only managed. A pressurized suit wants to expand into a sphere. That is what internal pressure does to any flexible container. The engineering required to fight that tendency, to maintain a shape that a human body can actually occupy and move within, involves joint designs and fabric geometries and bearing systems at every point of articulation, the shoulder that lets the arm rotate, the wrist that allows the hand to turn, the knee that allows the leg to bend. Each of these is a miniature engineering problem where the forces of internal pressure, the geometry of human motion, the weight constraints of something a person has to wear for hours, and the abrasion resistance required to survive the lunar surface all have to be satisfied simultaneously. They cannot all be satisfied completely. Every spacesuit ever built is a compromise, and the compromises show up in ways that matter operationally. The gloves are where the compromise is most visible. Human hands are precise instruments. The ability to apply fine force across a wide range, from the delicate adjustment of a fragile sensor to the torque needed on a stuck bolt, depends on direct contact between the fingers and the object being handled. A pressurized glove reduces that capability substantially. The Apollo crews returned from their moonwalks with blisters and abrasions across their hands, the result of working against the resistance of pressurized gloves for hours. The suit, pushing back against every grip and every pinch and every attempt at fine manipulation. The suit was not failing. It was doing exactly what it was designed to do. The problem was that what it was designed to do conflicted with what the hands inside it needed to accomplish. For a moon-based crew conducting multiple EVAs every week across a tour of months, the glove problem is not a minor discomfort. It is an occupational reality that accumulates over time, reducing the dexterity available for technical work that requires precision, adding fatigue to tasks that are already physically demanding, and compounding with every EVA until the cumulative toll on the hands becomes something that has to be managed as carefully as any other consumable resource. The dust interacts with the suit the way it interacts with everything else on the moon. It works into the joints that allow movement, into the bearings that permit rotation at the wrists and shoulders, into the sealing surfaces at every interface. The Apollo suits showed measurable wear in their mobility elements after the brief surface exposures of those missions. A suit used for repeated EVAs over months, in continuous contact with the abrasive particles that cover every surface on the moon, would experience cumulative degradation that inspection and maintenance would have to track without interruption. Every suit is on a clock from the moment it first contacts the lunar surface. The seal that is fine today will be slightly less fine after the next EVA, and slightly less fine after the one after that. The bearing that rotates smoothly now will rotate with slightly more resistance after another 30 hours of exposure. The visor that is clear when new will accumulate microscopic scratches that reduce contrast and create halos around light sources in ways that matter when you are trying to read instrument markings or assess terrain at the edge of your field of view. Tracking all of that, for every suit in the inventory, while also conducting the operational work of the base, is part of the maintenance burden that nobody discusses when the conversation is about the science a moon base could enable. Recent oversight assessments of NASA's next-generation lunar spacesuit development programs have repeatedly emphasized how difficult it remains to build a suit that can handle not a few symbolic steps on the surface, but repeated, technical work across many missions over an extended deployment. The challenge is not lack of effort or engineering talent. It is that the requirements genuinely conflict with each other at the margins, and resolving conflicts at the margins takes time and testing and iteration that the timelines of human spaceflight ambition consistently underestimate. You will spend more time in that suit than in almost any other single piece of equipment the base provides. It will be your constant companion on the surface, the thing between you and the environment every time you go outside to do the work that brought you there. It will fight you while you work and protect you while it fights you. It will wear and be serviced and wear again. A spacesuit is a compromise between movement and survival, and the moon attacks both simultaneously. There is a particular kind of problem that shows up in science when the act of observing something changes the thing being observed. Field researchers who study animal behavior know it. The moment a human being enters a habitat, the habitat is no longer quite what it was. The animals respond to the presence of an observer. The vegetation gets compressed along the paths researchers walk. Equipment placed in the field changes the local microenvironment in small ways. The data collected after entry is data from a place that the collection effort has already altered. The scientist trying to read a pristine record is simultaneously writing over part of it. The moon presents a version of this problem severe enough to deserve its own chapter. For 4.5 billion years, the lunar surface has been accumulating a record, not a record in any metaphorical sense, a literal physical archive written in layers of regolith, in the chemistry of ancient craters, in the distribution of frozen compounds in permanently shadowed regions, in the pattern of solar wind ions embedded in surface grains, in isotope ratios that carry information about the history of cosmic radiation stretching back to the formation of the solar system. The moon has no weather to erode these records. It has no tectonic activity to bury or destroy them. It has no biological processes to introduce contamination. What settled on the moon billions of years ago is, in many places, still there, preserved with a fidelity that nothing on Earth approaches. Scientists want to read that record. It is one of the strongest scientific justifications for sending humans to the moon with the capacity to stay and work. A trained geologist on the surface for months, ranging widely, making observations that robotic systems cannot replicate, collecting samples with the judgment that comes from years of fieldwork, could extract information about the history of the solar system that no orbital mission can provide. The science case for a moon base is not promotional language. It is real. The problem is that reading the record and building a base to read it from are in meaningful tension with each other. A moon base is not a quiet presence. It is a small industrial operation. Rockets land and launch, disturbing regolith across wide areas with every engine firing. Rovers drive across the surface, breaking the undisturbed crust of material that in some places has not been touched since it was deposited billions of years ago. Excavation equipment digs into the ground to access ice deposits and construction materials. The habitat sits on and is anchored to the surface, affecting the thermal and electrical environment of the material beneath it. Every piece of surface infrastructure creates a footprint that did not exist before, and the base breathes. Every operating habitat exhales. Air processing systems, vent gases, small amounts of water vapor and trace compounds leak through seals that are never perfectly tight over time. Rocket propellants leave residues. Every piece of equipment outgasses compounds from the materials it is made of, slowly, continuously, in quantities that are individually small, but that accumulate over the operational life of the base. Human bodies shed biological material and exhale compounds that have never existed on the lunar surface before. On Earth, these emissions disappear into an atmosphere that disperses them. The moon has no atmosphere in any meaningful sense. Molecules released from a base travel ballistically, following trajectories that carry them potentially kilometers from the release point before they settle back to the surface. The contamination footprint of a base is not a neat circle around its perimeter. It is a spreading region whose extent depends on the types of molecules released, the temperature of the surface, the activity of the solar wind, and the local topography in ways that are not yet fully characterized. Research into the contamination environment around operating lunar modules suggests that for some sensitive measurements, instrument placement needs to account for not just a few meters of separation from the habitat, but potentially tens to hundreds of meters. And in certain cases, particularly measurements trying to detect trace volatile compounds in the near-surface environment, the necessary separation may be measured in kilometers. The very science that provides one of the central justifications for building a base may require placing the instruments conducting that science far enough from the base that operating them becomes a logistical undertaking in itself. The permanently shadowed regions near the South Pole are among the most scientifically valuable locations on the Moon. They hold the water ice. They also hold the most undisturbed volatile deposits that exist in the inner solar system. Cold traps that have been accumulating and preserving chemical records since before the first life appeared on Earth. A base that mines those regions for water is simultaneously altering the scientific record that gives those regions their value. Every excavation disturbs stratigraphy that took eons to form. Every venting from the habitat deposits molecules into an environment that researchers want to sample for its native composition. There is a window of time that begins to close the moment the first rocket lands. The Moon before a permanent human presence is different from the Moon after one. Some of the most important scientific measurements available at the South Pole are best taken as early as possible, before the contamination footprint has expanded, and before the most sensitive measurements have been compromised by the operational activity of the base. The temptation to prioritize infrastructure development and crew safety over early science is understandable, and in many ways appropriate. But it comes with a cost that is easy to underestimate, and a cost that, unlike most of the other costs in this story, cannot be recovered. The original conditions of the lunar environment, once altered, do not return. There is also another way a moon base changes the Moon, beyond the science, beyond the contamination, in a way that is harder to quantify but no less real. From Earth, the Moon looks like an infinite grey surface, but a base cannot be placed anywhere. It needs light exposure, stable terrain, communication, geometry, proximity to landing zones, access routes, safe distances from contamination-sensitive sites, and some practical relationship to water ice. When all of those requirements are layered on top of each other, the Moon stops being an abstract grey world and becomes a landscape of better and worse locations. And better locations are never neutral for long. A landing zone becomes a port. A rover path becomes a road. A safety perimeter becomes a boundary. A crater holding water ice becomes not just a scientific archive, but a resource with an economic value. The Moon has no nations, but a base gives it neighborhoods. And neighborhoods require rules about who uses which landing zone, about how close one base can operate to another, about the safety perimeter around a science site that no one is supposed to disturb, about what counts as a fair claim to a location that everyone needs but not everyone can use simultaneously. These are not questions that belong to engineering. They are questions that belong to the species, and they do not stay abstract once the first base is operating. The first question of lunar science may not be what we can learn from the Moon. It may be how lightly we can touch it. When was the last time you went a full day without stepping outside? Not a day spent mostly indoors, moving between a car and an office and a store and back home. The kind of day most people have regularly. A full day where you never once felt outdoor air on your skin, never looked at a sky that was not behind glass, never stood somewhere without a roof over you, even for 30 seconds. Most people, if they think about it honestly, cannot name one, even on the most relentlessly indoor days. There is usually a moment, a walk across a parking lot, a few steps between a building entrance and a car, A minute on a doorstep waiting for a ride. Some brief contact with an outside world that exists independently of any human system, where the temperature was set by weather and not a thermostat, where the air came from somewhere that was not filtered and recycled. Now hold that thought and multiply the absence by 6 months. The first thing most people expect to hear about the psychology of long-duration spaceflight is boredom. And they are not wrong that boredom is a factor, but boredom is manageable. You can schedule around boredom. The harder things are the ones that do not announce themselves as problems until they have been building for weeks. Scott Kelly spent 340 consecutive days on the International Space Station between 2015 and 2016, the longest single spaceflight by an American at that point. He kept detailed journals and gave extensive interviews afterward. One of the things he came back to repeatedly was not the dramatic moments or the technical challenges or even the physical demands of living in microgravity. It was something quieter and more persistent. The absence of weather. The absence of a sky that changed. The absence of the small sensory variations that on Earth you absorb without noticing and that your nervous system uses, without your conscious involvement, to mark the passage of time and anchor you to a world larger than the one you are currently in. After a few months, he wrote, the station began to feel less like a place and more like a condition, something you were inside of rather than somewhere you were. A moon-based crew would face the same condition, and in some ways a more demanding version of it. The station orbits Earth every 90 minutes, 16 sunrises and sunsets per day, an artificial light cycle that the human circadian system handles poorly, but that at least provides constant visual change. Looking out the cupola of the station, you can watch weather systems develop across continents, watch the lights of cities scroll past at night, watch the Terminator line that divides day from night sweep across the surface of a planet that is always visible and always active below you. You are isolated, but you can see home. A moon base at the South Pole looks out at the lunar surface in every direction. The landscape does not change. The horizon is always the same distance away. If Earth is visible at all from that location, it hangs at a fixed point above the horizon, barely moving across the sky because of how the moon's rotation is locked to its orbit. It is there, but it is small, and it is far, and it does not feel like the same thing as seeing weather systems from orbit. Inside the base, the habitat is small. Early concepts place the usable volume for a small crew at somewhere between the size of a school bus and a modest apartment. The precise figure depending on the mission architecture, but bounded in every case by the reality that every cubic meter of pressurized volume was launched from Earth and cost money that competes with every other line in the program budget. 6 people in that space. For months. No private room to retreat to when you need to be alone with your thoughts. No corridor to walk down that leads somewhere new. No door you can open to step into a different environment. The research on group dynamics in confined environments is extensive and consistent in ways that matter for planning a moon base. It comes from Antarctic stations, where crews winter over in near-total isolation for months. It comes from submarine operations, where crews live in pressurized metal tubes with no access to the outside world for weeks at a time. It comes from the Mars 500 experiment, where 6 volunteers spent 520 days in a simulated spacecraft in Moscow to study the psychological effects of a Mars mission. The findings do not make for optimistic reading if you are trying to design a productive and harmonious crew for a moon base. Interpersonal conflicts in confined environments are not aberrations. They are expected features of the experience, as predictable as equipment wear rates, as built into the mission profile as the power consumption curves. The question is not whether they will occur. The question is whether they will be managed well enough to prevent them from affecting mission operations. Small irritations that would dissolve in a normal social environment, where people can separate and seek different company and have experiences that restore perspective. Instead, accumulate in confined spaces. A colleague's habit that is mildly noticeable in an office becomes genuinely difficult after 3 months of 24-hour proximity. A disagreement about procedure that would be resolved in a meeting and forgotten in a week takes on a different texture when the 2 parties involved will be sharing meals and sleeping 8 feet apart from each other until the rotation ends. The communication delay to Earth is small in absolute terms, about 1 1/3 seconds each way. Small enough that conversations feel almost normal, but almost normal is not normal. And after months, the subtle wrongness of every exchange with family and friends, the slight lag, the inability to interrupt and be interrupted the way conversation actually works, adds to the accumulating sense of distance between the base and the world it left behind. And then there is the awareness that does not go away. On Earth, most people move through their days without any background consciousness of their physical vulnerability. You do not, while making coffee or talking to a friend or reading at night, maintain an active awareness that you are a fragile biological entity dependent on specific environmental conditions for survival. The conditions are present and reliable, and your nervous system has learned not to spend resources monitoring them. On a moon base, the wall between you and a vacuum that would kill you in under 2 minutes is always there. You can see it. You can put your hand on it. The crew members who live there know, at some level that does not switch off during dinner or sleep, that everything sustaining them is machinery, and that machinery can fail, and that the distance between them and any meaningful help is 3 days at minimum and realistically much longer. That knowledge does not produce constant terror. People are more adaptable than that, but it occupies a background register of awareness that never fully empties. And carrying something in that register for months does things to a person that are not well quantified yet, because no one has done it long enough to generate the data. The sensory environment of the base offers no relief from this. Earth gives you rain, wind against your face, the smell of soil after a storm, which is produced by bacteria releasing compounds into the air as moisture arrives, and which the human nose can detect at extremely low concentrations. A sensitivity that makes biological sense, given how long humans have been using the smell of rain to navigate and to plan. The sound of leaves, the quality of late afternoon light in October, the sensation of grass or sand or uneven ground under your feet. None of these things are luxuries. They are the sensory vocabulary that the human nervous system evolved using, the background against which the architecture of human psychology was assembled over millions of years of existence in a biological world. Remove them for long enough and something shifts. Not a breakdown, not a crisis that shows up in any medical assessment. Something quieter and more fundamental, a kind of displacement from the conditions that the mind was built for, experienced as a persistent low-level wrongness that is difficult to name and impossible to entirely compensate for, with schedules and video calls and carefully designed habitat lighting that mimics a sunrise the crew cannot see. On Earth, outside is where we go to recover. On the Moon, outside is what the habitat protects us from, and no engineering solution can fully replace what the human mind has always known as a world. NASA calls it the Moon to Mars architecture. The language is deliberate. A moon base is not the destination in this framing. It is the preparation, the place where the technologies and techniques of long-duration surface operations are tested under real conditions, where the unknowns are discovered close enough to Earth that discovering them does not mean losing the crew, where the gap between what works in a test facility in Houston and what works on another world gets measured and addressed before the stakes are raised to a level where addressing it is no longer possible. The logic is sound. If you want to send human beings to Mars and keep them alive there for years, testing your systems on the nearest other world first is not timidity. It is the kind of thinking that prevents the kind of disasters that come from believing your models more than your experience. But follow that logic all the way through, with everything this story has covered, and something important comes into focus. The Moon is 384,000 kilometers from Earth. A transit takes roughly 3 days. The communication delay is about 1 1/3 seconds each way, small enough that conversations with mission control feel nearly normal. If something goes catastrophically wrong at a moon base, a rescue mission is theoretically possible within days. Not easy, not guaranteed, but physically possible within a time frame that leaves room for decisions to be made and acted on. Mars, at its closest approach to Earth, is about 54 million kilometers away. At its farthest, when the two planets are on opposite sides of the Sun, the distance exceeds 400 million kilometers. A transit takes 7 to 9 months in each direction. The communication delay ranges from about 3 minutes each way at closest approach to about 22 minutes each way at maximum distance. There is no rescue on any timeline that matters. A crew in trouble on Mars solves the problem with what they have, or they do not solve it. Mission Control can offer advice, but the advice arrives minutes after it was sent and the response arrives minutes after that. And a medical emergency or a cascading system failure does not wait for the round trip. Everything discussed in this story exists on Mars. The radiation environment is in some ways worse, because Mars has only a thin atmosphere offering minimal protection, and the 9-month transit to get there passes through deep space where Earth's magnetic field provides no shelter. The dust covers the entire surface and is distributed by weather systems, including storms that can last for months and cover areas larger than continents, reducing solar power generation to near zero for extended periods. The gravity is about 38% of Earth's, better than the Moon's 1/6. But the question of whether 38% is enough to sustain long-term human health has the same answer as the question about 1/6. Nobody knows, because nobody has been there long enough to find out. The logistics chain to Mars is not 3 days long. It opens at orbital alignment windows that occur roughly every 26 months. A component that fails on Mars waits for the next window, and then waits 7 to 9 months for the replacement to arrive. The spare parts inventory has to anticipate failures over a period measured in years, not months, without the ability to adjust based on what is actually happening until the adjustment is already months out of date. The crew cannot leave when circumstances demand it. A Moon-based crew facing a medical emergency has options. Difficult and costly, but real. A Mars crew is committed for the duration of the mission architecture that carried them there. And the alignment window that would allow a return does not open on request. The gap between needing to leave and being able to leave can be longer than the original mission was planned to last. A person describing a medical symptom to a doctor on Earth from a Moon base gets a response in about 3 seconds. The same exchange from Mars takes between 6 minutes and 44 minutes depending on where the planets are in their orbits. A consultation that feels nearly real-time on the Moon is an exercise in delayed correspondence on Mars. And every minute of that delay is a minute during which the patient is managing the situation without the guidance they are waiting for. The point is not that Mars is impossible. The history of human achievement does not support the idea that impossible is a stable category. The point is that the Moon, with all of its challenges, with everything in this story that has tried to give those challenges their actual weight, is the easier problem. It is the problem where rescue is theoretically possible, where communication approaches real time, where the resupply cycle is measured in months rather than years, where the consequences of being wrong can sometimes be corrected before they become irreversible. If the Moon reveals that our life support technologies degrade faster in the actual lunar environment than they did in testing, that information is recoverable. We learn it. We redesign. We improve. If the same revelation happens on Mars, the crew that provided the data may not be in a position to benefit from the redesign. If the Moon reveals that human beings in 1/6 gravity over a year experience physiological changes that the exercise protocols were not preventing, that information changes the protocols and changes the mission planning for what comes next. If the same revelation happens on Mars, the crew is 9 months from any meaningful intervention, in a direction that the intervention would have to travel. The Moon to Mars architecture is built on the premise that the Moon teaches lessons that Mars requires. That premise is correct, but the lessons only transfer if the Moon program is honest about what it is actually learning. If the schedule pressure and the budget pressure and the political pressure to show visible progress produce a program that calls things solved before they are solved, that moves to the next phase before the current phase has generated the understanding it was supposed to generate, then Mars inherits all of the Moon's unresolved problems at a distance and on a timeline that removes almost every margin for error. There is a version of this story where the Moon and Mars are sequential chapters in a genuinely expanding human presence beyond Earth, where the difficulty of the moon is met honestly, and the knowledge accumulated there compounds into real capability. That version is possible. Nothing in the physics or the engineering or the biology prevents it. What it requires is the willingness to let the moon be as hard as it actually is, rather than as easy as the program needs it to be. The moon may not tell us whether Mars is impossible. It may tell us whether we are honest enough to know what we are truly asking for. On Christmas Eve of 1968, a spacecraft called Apollo 8 became the first crewed vehicle to reach lunar orbit. The mission had not been designed to produce the most reproduced photograph in history. The three astronauts on board, Frank Borman, Jim Lovell, and Bill Anders, were there for technical objectives, test the navigation required for a future landing, demonstrate that the spacecraft could make the journey and return the crew safely. The mission planners had not scheduled time for photography of Earth, because Earth was not the destination. The moon was the destination. Earth was just the place they had left. Then, on the fourth orbit, Bill Anders looked out a window and saw something that nobody had thought to plan for. Earth was rising above the lunar horizon. He knew it was going to happen. The geometry was not a surprise, but the sight of it, the actual experience of seeing his home planet as an object, a small vivid sphere of blue and white suspended in absolute black above the grey lunar surface, was something that no amount of intellectual preparation had made him ready for. He scrambled for a colour film magazine, almost dropping it, and took a photograph that people who were alive in December of 1968 remember seeing for the first time, the way they remember where they were when they heard certain pieces of news. He had gone to explore the moon and ended up discovering the Earth. That sentence is not a metaphor. It is what happened, and it has been happening, in one form or another, to everyone who has travelled far enough from this planet to see it whole. Edgar Mitchell, who walked on the moon on Apollo 14, described standing on the lunar surface and looking back at Earth and feeling something he later spent years trying to put into words. A sudden, visceral awareness of the planet as a single system, an understanding, not intellectual but felt, that everything he had ever known or cared about existed within the thin, bright line of that atmosphere, that everything the species had ever done or suffered or built or lost had happened on that small sphere. He said afterward that he had intended to go to the moon and come back a test pilot. He came back something else, though he was never entirely sure what to call it. The astronauts who followed had versions of the same experience, not identical, because people are not identical, but consistent enough that the researchers who study the psychology of spaceflight have given it a name. The overview effect, the cognitive shift that occurs when a human being sees Earth from enough distance to hold it all in a single field of view, and the categories that seem to organize the world, the borders and the distinctions and the priorities, suddenly look different in relation to the fragile and irreplaceable whole that contains them. What this has to do with a moon base is not immediately obvious, but it is the thread that connects everything in this story to something larger than engineering. Think about what the moon lacks. No atmosphere to breathe or to soften the radiation or to burn up the debris that arrives from space. No liquid water on its surface. No magnetic field. No biological activity of any kind. No weather that follows any pattern a human nervous system was built to read. No outside that is safe to step into. No sensory environment that the human mind evolved to inhabit. The moon is, in the most precise and literal sense, a world that was never designed for life. A world where life has never existed. A world where every condition that living things require is absent by default and must be created and maintained at continuous cost. That list is not a description of the moon's deficiencies. It is a description of Earth's gifts. Every item on that list, the atmosphere and the water and the magnetic field and the biological cycles and the weather, and the outside you can step into and the sensory world that your nervous system evolved in, is something that Earth provides automatically, continuously, without being asked, without a maintenance schedule, without a power budget, without the possibility of a cascade failure that kills everyone who depends on it. You inherited all of it. Every human being who has ever lived inherited all of it. It is the starting condition of human existence on this planet, so fundamental and so constant that it disappears from conscious awareness entirely. The way the floor disappears from consciousness the moment you learn to walk. The moon removes the floor, and when the floor is gone, you can finally see it. There is a version of this story that ends with a simple conclusion. The moon is too hard. The challenges are too great. The costs are too high. Go back to Earth and appreciate what you have. That version of the story is not this one. And not only because it is wrong about the conclusion, building a moon base, if it is done honestly and carefully and with full acknowledgement of what it actually requires, would force the development of technologies and capabilities that have value far beyond the moon itself. Closed-loop life support systems that waste nothing and recycle everything. Medical protocols for humans in novel physiological environments. Radiation mitigation strategies. Psychological frameworks for small groups in extreme isolation. Power systems that work in the harshest environments. Construction and manufacturing techniques that function with minimal resources. Every one of those capabilities has applications on Earth that matter enormously, in places and circumstances that are not on the moon, but share the moon's quality of being, environments where existing systems are insufficient. The technologies that would keep a crew alive in a sealed habitat in 1/6 gravity might keep a research station viable in the deep ocean, or a habitat functional in a permanently flooded coastal region, or a medical system running in a place too remote for conventional infrastructure. The moon base would also, if it succeeds, demonstrate something about what the species is capable of when it commits to solving a genuinely hard problem with full honesty about how hard the problem is. That demonstration has value that does not show up in any budget calculation, but that is not trivial. What it cannot do, and what this story has tried to make clear, is succeed on inspiration alone. The enthusiasm that generates funding and political support and public excitement is real and necessary. It gets the program started. It does not, by itself, solve the dust problem, or the radiation problem, or the spare parts problem, or the question of what 1/6 gravity does to a human body over 2 years. Those problems require the slow, careful, unglamorous work of finding out what is actually happening and being honest about the gap between that and what the models predicted. Harrison Schmitt sneezed in the cabin of Apollo 17 in December of 1972, and the symptoms faded and everyone moved on, and nobody was able to study what lunar dust exposure means over months because nobody spent months there. That small unresolved question, and the hundreds of others like it, are the real legacy of Apollo in the context of what comes next. Not the flags, not the footprints, the questions that the brevity of the visits prevented from being answered. Gene Cernan stepped off the lunar surface on December 14, 1972, and sealed the hatch, and became the last human being to stand on the moon. In the more than 50 years since that moment, no one has gone back. The dust has been settling on the retroreflectors. The permanently shadowed craters have been holding their ice. The surface has been accumulating impacts one by one, patient and indifferent. Exactly as it was doing before the first Apollo lander touched down, and exactly as it will be doing long after the last human visitor has departed. When we go back, we will bring with us everything the moon lacks. The air and the water and the warmth and the biology, boxed up in machines that must never stop working, carried there at enormous cost by people who will live inside those machines for months, and emerge periodically into a landscape that may never feel like home but that they chose anyway. And perhaps, in the middle of some ordinary day at the base, during a routine maintenance check or a scheduled EVA, or an evening meal with 5 people who have become more familiar to each other than anyone else on the planet they all came from, someone will look out through the habitat window. Earth will be there, small, blue, vivid in a way that photographs do not capture, because photographs cannot convey the fact of seeing your entire world, everything you have ever known, every person you have ever loved, every place you have ever been, contained within something small enough to cover with your thumb. And in that moment, before the next system check or the next task on the list, Something that was always true will become briefly and completely visible. The atmosphere that softens the sun and carries weather and lets you breathe outside without equipment. The oceans that regulate the temperature of the entire planet. The magnetic field that deflects the solar wind. The 4 billion years of biological activity that transformed a ball of rock and gas into something capable of sustaining the existence of a creature that can look back at it from 250,000 miles away and understand, for the first time fully, what it is looking at. Maybe the first true lesson of a moon base is not how to live away from Earth. Maybe it is how to finally understand what Earth has been doing for us all along.